How many terms of the series um, is it necessary to take to find an approximation that's correct to within 0.001? So here what's happening is we have an alternating series. S sub n is 1 over so S sub n is 1 over k squared, and S sub n plus 1 is 1 over k plus 1 squared. But what we want to do is we want to find how many terms do we need to take to find an approximation of this series correct to within 0.001. So remember, the fact before we use the alternating series remainder estimation theorem, what we have to do is we have to show that this alternating series converges. All right. So which means we have to show that S sub n plus 1 is less than S sub n. Basically, we have to show that 1 over, and because k is greater than or equal to 1, then 1 over k plus 1 squared will be less than 1 over k squared. Hence, we can say S sub n plus 1 is less than S sub n. That's one of the conditions, when you're testing for convergence of an alternating series. And then the other thing is what we have to show is the limit of S sub n as n approaches. So the limit of S sub n, which is 1 over k squared, as k approaches infinity. And by the way, this limit will be equal to 0, okay, as k approaches that limit, which means that this series converges. Hence, we can say this series from k is equals to 1 to infinity of negative 1 to power k minus 1 over 1 over k squared converges by alternating series test. Okay, now that we've confirmed that, we can now apply the alternating series estimation theorem. And what does the alternating series estimation theorem say? It says that the remainder is less than the first neglected term. So we can say since the remainder is less than, so let me just write here properly, since the remainder is less than the first neglected term, then actually don't have, yep, that's fine. Then S sub n plus 1 will be less than 0.001. What I mean here is, since the remainder is less than S sub n plus 1, then it means that S sub n plus 1 will be less than 0.001, right? Because we want to find an approximation correct to within 0.01. Okay? So since the remainder is less than S sub n plus 1, then S sub n plus 1 is less than, for Sn to be accurate, to within 0.001. Okay, so what you're going to do is we are going to form an equation in terms of S sub n plus 1, an inequality that you're going to solve, and use that to find what n is. So what I mean is that using this, inequality. Remember, we know what S sub n plus 1 is. Up here, we have what S sub n plus 1 is. All right? We know what S sub n plus 1 is. So what I'm going to do is I'll just write S sub n. Let me use the blue one. S sub n plus 1 is less than 0.001. But S sub n plus 1 is 1 over n plus 1 squared, which is less than 0.001. Now, if you take the reciprocal of this, right, then I'll end up with n plus 1 squared will be, now if you take a reciprocal, the inequality changes, which means that will be greater than, the reciprocal of 0.001 will be 1,000. And then you can just get the square root, so n plus 1 will be greater than, now the square root of 1,000 is 31.6, which means n will be greater than 30.6, and hence n will be equal to 31. Okay, so that's how you apply the alternating series estimation theorem to solve a problem like that one there. I'm going to move to example 8. Now, show that this alternating series converges and find the sum of the series with error less than 0.0001. So that is about 3 decimal places. So our cutoff point is after 3 decimal places. All right, so our answer basically should be accurate to 3 decimal places. Our sum of the series should be accurate to 3 decimal places. Now, the first thing that we have to do is we have to find, we have to show that this series converges by alternating series test. So S sub n is 1 over n to the power 4. S sub n plus 1 is equal to 1 over n plus 1 to the power 4. So what I'm going to do is, first of all, to show that S sub n plus 1 is less than S sub n. And because n is greater than or equal to 1, it makes sense that 1 over n plus 1 to the power 4 will be less than 1 over n to the power 4. So hence S sub n plus 1 is less than S sub n. And then the next we have to find the limit. So the limit as n approaches infinity of 1 over n to the power 4, and that will be equal to 0. Hence, we can conclude and say that this series a lot of writing here. This series converges by alternating series test. Alternating series test. And then after that, what I'm going to do next is to apply the alternating series estimation theorem. Now, from the question that stated that the error should be less than 0.001. And then I'll write the same statement that I wrote previously. And what I said was that since R n, the error is less than S sub n plus 1, and here we are trying to find the sum of the series with the error less than 0.0001, it means that S sub n plus 1 is less than 0.0001. Okay? So since the remainder is less than S sub n plus 1, then S sub n plus 1 is less than 0.001. For the sum for Sn to be accurate, to within 0.0001. Okay, so now what you're going to do is to form that, write down that inequality in terms of these guys here. We have that, all right? And by the way, we have what S sub n plus 1 is. So what I'm going to do is to write that inequality, which will be 1 over n plus 1 to power 4, which is S sub n plus 1, is less than 0.0001. So which means that n plus 1 to power 4 will be greater than the reciprocal of that, which happens to be 10,000. So n plus 1 will be greater than the fourth root of 10,000, which is just 10. So n will be greater than 9, which means n will be equal to 10. Okay, they want us to find this sum, right? And find the sum of the series. So we need to find the sum of the first 10 terms. So we need to find the sum of the first 10 terms. Now, to find the sum of the first 10 terms, what you can do is you can just use your calculator. So if you go onto your calculator, you can calculate the sums of these guys here. So go on to Y1 and then press math, scroll down to summation. So from x is equal to, from x is equals to 1. Now I guess you have n is equals to 1. To x, instead of infinity, just write x, because what we want is a finite value. And then what we have here is just plug in the nth term of this series. So alpha y is equals to, I'm looking for the fraction bit, then -1, use brackets, 2 power n, so 2 power x, and then we have x to power 4. Always check that everything is correct. All right, and then what you can do is just go onto the table. So second, that bit, you go to the table, and you should be able to find the value of this series. So what we want is S10. So the sum of the first 10 terms of the series, which is equal to that. Okay. And you know, to 3 decimal places, that will be equal to negative 0.947. And if you inspect, if I move along, you know, keep going. Remember, we are saying that the error is less than 0.0001, and which means that n is greater than 9. So any number greater than 9, the sum will be equal to, will be accurate to within 3 decimal places within 0.001. So if you scroll down, you can see that the sum of the first 13 terms correct to 3 decimal places is the same answer, negative 0.947, all through. All right, because the error is less than 0.001. So anyway, our answer will be negative 0.947.